Okay, 23.2, comparing linear, exponential, and quadratic models. So here it's taking data and trying to figure out what is going to be the best fit in terms of type of graph for the information. Now, one thing to note is the difference in the end behavior for each of these. Okay, so for a linear, there's infinite behavior on both ends as x approaches negative infinity, as x approaches positive infinity. The thing about a linear, though, is that typically they're going to be in, well, not typically, always, they'll be in different directions. So end behavior on one end is positive infinity, end behavior on the other end is negative. Whereas with a quadratic, it has infinite behavior on both ends, but it's in the same direction. So here they're both positive infinity, or if our parabola was going down, it would be going to negative infinity on both ends. Whereas an exponential, we've seen that it has end behavior towards infinity on one end, but flattens out at 0 on the other end. So, or some sort of constant you'll learn in Algebra 2. So, different behaviors. Okay, so again, end behavior, linear has infinite behavior on the ends, but they're different. One's positive, one's negative. Quadratic has infinite behavior on the ends, but they're both in the same direction, both positive or both negative. And then an exponential has infinite behavior only on one end, and then the other end is towards some sort of constant. Typically, in our case, is 0. Alright, so one other thing I wanted to point out here is a fastest growing function is always going to be an exponential. Exponentials grow faster than either a linear or quadratic. Okay, that's because our exponent is our variable, whereas in these, our variable is a base. Our exponent is either 1 or 2. So having a variable that is your exponent, then if x is 1,000, then your exponent's 1,000. That's obviously going to go a lot faster. All right, so let's look at some examples. Here I want to point out something to help you understand how you identify a quadratic regression in terms of values. You take the y values and you subtract them. So if you subtract 1.5 minus 3, you get negative 1.5. Okay, but then to see if it's a quadratic, you take the second difference. So you take these differences and then you subtract them. Negative 0.5 minus 1.5 is 1. 0.5 minus 0, or negative 0.5, I can't talk, is also 1. The second differences are constant. When the second difference is constant, then that means it's a quadratic. Okay, another way to look at this, when we looked at comparing them, remember linears, they always go up by the same amount every time. Quadratic or exponentials, on the other hand, have the same ratio. They're multiplied by the same thing every time. A quadratic is always going to go up by the same amount on the second time, and the reason it's referred to as the second difference is because of being to the second power. Alright, so here's our first problem we're going to do. So they give us a set of data, and they give us the points, and they want us to plot these points, and then take a look at the graph itself to help us kind of determine what's a better fit in terms of the type of model it is. So all I'm going to do here is I'm just going to plot these points real quick on the graph. So we have 0, negative 4, 1, and negative 3.8, and 2, negative 3.2, and negative 2.2, and 4 is negative 0.8, 5 is 1, and then 6 is 3.2. Okay, so if we were to connect those, kind of looks like that. Okay, all right, now if we look at it in terms of just one side, you might initially think, this could be a exponential. If you think on this end, that it just flattens out. That's what an exponential would look like. But because we don't really know what the behavior is on this other end, it could actually do something like this and curve up, and then it's a quadratic. What we do know is that it's not a linear. It's not a linear. So the way they want us to determine this is algebraically by doing the second difference. Okay. So what's that mean? We're going to take the values here and we're going to subtract them. So the first thing I'm going to do is I'm going to subtract this one minus that one. If I do that, I get 0.2. Then I'm going to subtract this one minus this one. If I do that, I get 0.6. Okay, and then I just keep on with that. So I get 1. And then for the next one, if I subtract negative 0.8 minus negative 2.2, then I'm going to get 1.4. Okay, then I do the next one, and I'm going to get 1.8, and do the next one, I'm going to get 2.2. So the second difference is basically this. What's happening here every time? Well, if you're good and you can see decimals, it's going up by 0.4, 0.4, 0.4, 0.4, 0.4. That second difference is the same. Therefore, this is actually represented by a quadratic model. We're just not seeing the second half of the quadratic. We're only seeing the positive side. So that's why you can't always just look at a graph and determine, because you got to see more of the graph to know exactly what it is. So that's that end behavior and seeing what's happening here. Okay, let's keep going. So again, they give you some more examples here, and we're going to jump right to this next year term problem. So it's kind of the same thing. It says determine the function represented in the given table is quadratic or exponential, plot the given points, analyze the graph, draw a conclusion if possible, then find the first and second differences and ratios, and either verify your conclusion or determine the family of function. Okay, so this time we're also going to do algebraically the ratio. So first let's do the difference. So the difference is this minus this. Okay, so here I am going to use my calculator. So I've got negative 3.11 minus a negative 5, and that's 1.89. Then I'm going to do this one minus this one. So negative 1.44 minus negative 3.11. I get 1.6, 7. The next one I know is going to be 1.44. That's an easy one. And the next one I know is going to be 1.22. So easy. And then I get 1. And then I'm going to get, I think, 0.78 is correct. And then 0.56, 0.33, and then 0.11. Okay, so we take the second difference. In other words, now we're going to subtract this minus this. So if I do that, that's going to give me 0.22, actually negative. Then I do this minus this, and that's going to give me negative 0.23. Then this one minus this one, negative 0.22, negative 0.22, negative 0.22, same, going down to 2. This next one's negative 0.23. The next one is negative 0.22. So you look, this is almost identical. Okay, so this is probably going to be a quadratic again, but they want you to verify it by doing a ratio. So this time what we want to do is look back, think about how we compared exponentials. So now for this one, what it wants me to do is it wants me to take this term and divide it by that term. So I'm going to write it out so you know exactly what I'm typing in on the calculator, over negative 5. So I'm typing that in on the calculator, and that gives me 0.622. So I'm going to erase that now, and I'm going to put 0.622. Then I'm going to do it again. This time I'm going to do negative 1.44 divided by negative 3.11. And I get 0.463. So that's already a great indication this is not an exponential, because if it were, these ratios would be the same. What am I going to get in the next one? 0 divided by negative 1.44 is 0. Okay. Do the next one. Can't do it. It's an error. Okay. You can't divide by 0. If you do 1.22 divided by 0, your calculator's going to say error. It's not possible. So that tells me this is not an exponential. It's got to be a quadratic. Now, what we're actually going to do is, and you could draw the points on the graph, and since you know it's a quadratic, you know it would curve up on the other end, you know it's going to have infinite behavior on both ends. These are all going up, so that means since our values here are increasing as x goes to negative infinity, y is going to infinity, but also as x goes to positive infinity, y is going to infinity. Remember what we said with quadratics. The infinite behavior is in the same direction on both sides. We just got to figure out, is it going positive or is it going negative? And again, because our values here are going up, it's going to positive infinity. Okay. So what we want to do next is we actually want to do this using a calculator. So I'm going to go to this next your term problem, and we're going to use the calculator to help us come up with all this stuff. Okay. So what I want to do is I'm going to type this data in to the calculator. You may have to go back and refer to previous modules. I think it was module 16 where we did exponential regressions. It may have been module, I'm trying to remember, 19 or 20 where we did quadratic regressions. Linear regressions were way back, like in module 4 or something like that. So you got to remember how to do these on the calculator. So I'm going to try to walk you through it again real quick here. Hopefully this will all make sense. First thing, you never type a year in. We've talked about this before. If this is our starting year, that's actually our 0 term. This would be term 10 because it's 10 years away. And this would be term 20, so forth and so on. So the first thing I'm going to do, I'm going to reset my calculator. I'm going to go to my mode. I'm going to turn my stat diagnostic on. I'm going to press the stat button. It's going to come up edit. I'm going to press enter. I'm going to type my data in. So I'm going to type in 0 for L1, then 10, then 20, then 30, 40, 50, 60, and then 70. Okay, so make sure that's right. 0, 10, 20, 30, 40, 50, 60, and 70. Okay. Go over to L2 now and type in your other data. 21.2. Now, one thing to remember is when we do this problem, this is representing a percent. 24.2, 30.8, 32.5, 32.8, 32.3, 31.4, and 30. Okay. Now, once we've got our data entered in, then we go back to stat, right arrow over to calculate. Now, what I'm going to do is I'm going to do each of the different models, and we're going to look at the R, the correlation coefficient, and then we're going to evaluate them. Okay, so I'm going to slide this up a little bit. So I'm going to do my linear regression first, linreg. So under calculate, this is number 4. And I'm going to get my equation. So y equals, I'm going to go down to 4. I'm going to calculate it using my two lists, and I get 0.1219x plus 25.13 repeating with an R of 0.692. That's not a very good fit, okay? So let's go to the next one. Let's do a quadratic regression. So all I do here is I go right back to stat, right arrow to calculate, But this time I'm going to do number 5. So a quadrag. So this is number 5. So y equals. So I press that one, go to calculate, and I get y is negative 0.006 x squared plus, I'm going to run out of room, so I'm going to have to write under it, 0.546 x plus 20.89, and this time we don't have a correlation coefficient of r. Instead we have this r squared. Well, in this case, this is representing what our correlation coefficient is, and the reason it's r squared is because, think about it, it's a squared function, okay? So here we have 0.953. That's a lot closer to 1. That is a lot closer to 1. So that seems to be fitting our data. It's also squared because there is no negative in this case in terms of quadratics. Quadratics can be either increasing or decreasing, but because it either opens up or down. So in this case, we would say it's opening up, and we'll explain that based on the data. The last one I'm going to try is the exponential regression, which is number 10. So I go through and do the same thing, stat, calc, go down to number 10, exponential regression, calculate, and I get y is 24.74x plus, that's writing it as a linear, my apologies, 24.74 times 1.005, that would round to 5, to the x power, because it is increasing. It's not increasing much, and I'll tell you why here. So r here is 0.703, not a very good fit. So obviously this is a quadratic. But I wanted to go back and reevaluate the points and kind of give you another indication as to why I knew this was a quadratic. If I take this point right here, remember with quadratics we said there's a repeated pattern on either side. Well, these points are pretty close together. And then you come down here, those next points are close. In other words, it's doing the same thing on the opposite side. So it's almost like this is the vertex right here, this point. It's not, but it's kind of like the vertex, and then the pattern repeats on either side of it. That's what a quadratic does. Whereas with an exponential, it just keeps increasing on one side or decreasing. And same with a linear regression. So that's using the calculator to come up with which is the best fit by just doing the regression equations. So you have another example here. You could put the data in, find the same sort of thing. Hopefully, though, you can kind of look at it. Okay, what's happening here? Increase, increase. Okay, we're increasing the whole time. It's just a matter of how it increases. So again, you put your data in and you can get a fit. You can draw the graph. Think about in behavior and all that stuff. This will be stuff that you continue to expound on in Algebra 2, but hopefully using the calculator will help you quite a bit with this.